Okay, let's take a look at this check on free energy and equilibrium. So we've been looking at free energy, delta G, and now we have to kind of combine that with our understanding of equilibrium. So the equilibrium point occurs at the lowest free energy value available to the reaction system. That's kind of the classic statement there. And so we're going to take a look at some of these scenarios. And we have an equation. Let's write down our equation here. Okay. So EQN for equation. And our equation that we want, there's actually two variations of this. Delta G under standard conditions is equal to negative RT natural log of K, equilibrium constant. We can also turn that around if we're wanting to find K, and we can take that as e to the negative delta G divided by RT. Okay, I don't remember which one is listed on your formula sheet, so you might want to look at that and see which one you're more comfortable with, because I think only one of those two. I'd have to go back and look. All right, so here are some different scenarios for delta G versus K. So when delta G is 0, K is 1. Okay, and the reaction doesn't really favor either side, of course. If it's 1, that means that the forward and the reverse are both equivalent. And if delta G is less than 0, then K is going to be greater than 1, and then that's going to favor the products. It's an exergonic reaction. And then vice versa, if delta G is greater than 0, then K is going to be less than 1, and then it's going to favor the reactants. And you can kind of plug that into a generic equilibrium constant expression if you ever forget those, and kind of look at how that might work to see which way it would favor. So let's go ahead and take a look at a situation here where hydrogen sulfide can be removed from natural gas by this reaction, and we're asked to calculate delta G and K at 298 Kelvin. So the first thing, I just want to kind of take a look at our equation here and just realize that I have 3 moles of total gas on this side, 2 plus the 1 here, and then on the other side, this is a solid, and so we don't have a homogeneous situation, so I only have 2 moles of gas. Okay, when we're looking at gases. Okay, so let's go ahead and come down and do some calculation work here. So delta G for this particular situation, we're going to go back and use some of those values that are in the appendix. Okay, so we're going to do that sum of the products minus the sum of the reactants. Okay, so I went ahead and pulled those numbers already. Of course, the O2 is going to be 0. I like to write that out still, just to make sure that I am accounting for, or the SO2, I believe, is the one that, nope, the S, sorry, products. Here we go. That's going to be 0. There's where my 3 is. But I always like to represent it anyways. So you can go back and double check all of these values in the appendix if you want to, just to make sure all of those are in there. And so when I calculate all of that out, I get a delta G value at standard conditions of negative 90 kilojoules per mole, which is also, because we're going to use that R value, in joules per mole Kelvin, we can say that's also equal to negative 90,000 joules per mole. Okay, so that gives us our delta G value under standard conditions. So that is this aspect of the problem. Now let's go ahead and solve for our K value. Okay, so for K, we're going to solve. So we can plug this in a couple different ways, but I'm just going to go ahead and write it out how I kind of normally think of this. So I'm going to take my negative 90,000 joules per mole. And remember the R value that we're using. Okay, and I guess I should probably put this up here again. Our R value that we're going to use is going to be the 8.314 joules per mole Kelvin. Okay, so I'm going to plug that number in down here. And we're going to have that negative at the very beginning. So I'm going to put a negative sign there. So negative RT natural log of K. So I'm going to have my 8.314 joules per mole Kelvin times the 298 Kelvin, okay, and times the natural log of K. All right, so if we want to rearrange this, we can, or we could use that other equation. So you can kind of set it up either way, because you can end up using the K equation, and so eventually you end up setting it up that way. I'm going to go ahead and just solve this way to get our number that we would raise that exponent to. I'm having a hard time writing that today. Okay, we're going to get a positive number, so 36.3 is what I calculated that ahead of time to be. So K then is going to be equal to E to the 36.3. And when I plug that in to the calculator, I got 5.9 times 10 to the 15th. These numbers sometimes seem crazy ridiculous, really big numbers, but that's okay because we are using that and solving it properly when it comes to this. Okay, so sometimes Moser's made up numbers are for a problem will give us some kind of crazy numbers in that. All right, and then the last question I actually think is really, really good. So would the reaction be favored at high or low temperatures? And so this is kind of a thinking question. We have to go back and consider how this works. So let me kind of break this down because I have seen these types of questions pop up a variety of times. So remember, our delta G is equal to delta H minus T delta S. Okay, so let's consider this. In order to have this reaction be spontaneous, it has to be a negative delta G. Okay, so negative is spontaneous or thermodynamically favorable. Okay, so if in this particular situation we have a delta H that is negative, okay, because it's exothermic, and one of the reasons we would know that is when we go back and look at our K values, we see that if it's larger than 1, it favors the products and it's an exergonic reaction. Okay, so this is how I know that. It's exergonic. I'm going to assume that it's going to be a negative enthalpy. I probably shouldn't make that assumption, but for right now I'm going to. And then we know because we've gone from 3 moles to 2 moles, okay, it's also going to be a negative delta S. Okay, so the question then becomes, what has to happen with T? This is our question, right? We need to know what has to happen with T. Well, since this whole situation on this side gives us this expression of a negative value, okay, our T has to be a low temperature. Okay, so why? Well, if we're going to subtract and we know that the delta S is negative, that means whatever we get for T and we have a negative delta S is going to itself be negative. So we're going to have a negative value for whatever this is. We'll just call this X. Okay. If we have a high T, then that's going to give us so this is a negative in there, so plus whatever that would be, X. If it's going to be too great, we wouldn't end up with a negative delta G. So that means we have to have a relatively smaller number, okay, or a lower temperature in order to maintain that to be a value that's going to give us an overall delta G that would be spontaneous. So I'm going to write over here, let's grab a different color, favored at low temperature temps. Okay. Kind of keep that in mind. You might look at it a little bit differently, but I've found that there have been quite a few questions I've seen pop up over the years that have asked questions similar to this, not necessarily for a value, but for the which direction would be favored. And we've kind of looked at that before with some other scenarios, but keep that in mind. And you can always put in some arbitrary numbers if that makes it easier for you. I find that when I'm confusing myself with those, that's actually my best practice, is to put in some arbitrary